what you're going to do is you are going to determine the molarity. That is the concentration, not the strength. Both of the chemicals you're using today are strong. You'll have a strong acid, hydrochloric acid. You'll have a strong base, sodium hydroxide. Now, if you have a base, can you add acid to it to neutralize it and turn it to salt and water? Yes, and that's what you're going to do. Squilly up here has the sodium hydroxide. He is going to don all his protective gear. He's going to measure out using the graduated cylinder 25 milliliters of sodium hydroxide. He's going to then dump that into your beaker. You should have a beaker out there back at your lab that's labeled sodium hydroxide with a question mark molarity for it. That means you don't know what it is. It could be 5 molar, in which case you wouldn't ever want to touch it. It could be 0.25 molar, in which case it is dangerous for you to mess with, but it isn't going to burn the heck out of you. All right? And you don't know this, so treat it like it's the 5 molar. You are then going to go back. At each table there is a squeeze bottle. Please don't turn those squeeze bottles up to squeeze in your hydrochloric acid. Otherwise they're going to drip on you. And you drip, we got to stop the lab for you and clean it up and wash everything off, because these chemicals will burn you. You're going to fill up your burette. That's B-U-R-E-T, burette. Fill it up to the top, which is usually 0. And then there's a stopcock on it that when it's turned 90 degrees to the burette, it's off. As you turn it so it's lined up with the burette, it'll be on and dripping. You will drip acid into your base until the base becomes clear. When it transitions from its pink, purple, fuchsia, I don't care what you call it, phenolphthalein color to clear, you will know that it has completely come to the equivalency point. It'll be water and a salt, and then you will know how much of that known hydrochloric solution, 0.2 molar hydrochloric, you used, and you can then figure the molarity of your unknown sodium hydroxide. Start with the chemical equation of what we're doing. We are taking hydrochloric acid, we are combining it with sodium hydroxide, which produces a salt, in this case sodium chloride, and water. Is that a balanced chemical equation? Yes, sir. It is a balanced chemical equation, and I chose this one because you don't need to worry about stoichiometry at all. Your coefficients are all 1. Now you get that done. Okay, you got this drawn. This is your apparatus. This is how it's going to set up. You're dumping hydrochloric acid into sodium hydroxide to neutralize it. You are going to figure out how many milliliters of hydrochloric acid it takes to do this. So whatever your top line is, whatever your end line, you subtract them from each other and you get how many milliliters you used. The equation, now down below this, draw on this, put this. Your known is your 0.2 moles of hydrochloric acid. Your unknown are your moles of sodium hydroxide. If you take the molarity times the volume, I even made it so you could do this in milliliters instead of converting it to liters. your moles times your volume of your known will equal the moles times the volume of your unknown. If you figure out and measure using your burette the volume of this, and you know the volume of this is going to be 25 milliliters, can you figure this out?
Yes.
Yes. And the way you do that, here you have 0.2 milliliters of, you're going to figure this out using your burette, equals the molarity that you want to try to find out times 25 milliliters. Of course, you want just the molarity, that's what you're solving for, so you divide both sides by 25 milliliters. Your milliliters cancel out and you end up with molarity. Molarity of your sodium hydroxide. All right, are there any questions about this? Yes, sir.
So in the milliliters that is blank, we would find that in the burettes.
Yes. How much hydrochloric did you use to neutralize that sodium hydroxide? This is the indicator.
How much? Oh! Okay. So if it turns back to like normal color, Rasmussen will be neutral.
Ours will be here in the
It'll be neutral.
When it turns back to like
So it's
clear.
just salt and water.
Okay.
So I open this?
No, yeah, wait. We need it. So what is this at? It's about at 0. All right. So now.
It's actually just at 0.
Yeah, same thing. About same here, cool.
very important part of your life.
Take it right to the top. Even.
Oh!
Damn, be careful with that stuff. It is dangerous. All right. Now swizzle every time.
Yeah.
Don't overshoot like that.
Yeah. You can really just take it down to 40 because that's where it's at.
Open.
40.
Hey, Angel, you want some salt and water?
45!
It's only salt and water.
Stick your finger.
The mixture of that.
See it burns your
Yeah.
finger off.
Have you ever seen the Bride of Chucky? Ah!
Just kidding. Say what?
As that just starts burning, starts sizzling up.
What was that? Water?
You're kind of scared right now.
It feels funny. That's why.
Yeah. You're losing that finger.
What's it smell like?
Are we supposed to do this?
Really?
Smell it.
No.
At first, I didn't think it was.
There's a thing called wafting, guys. Not stick your freaking hand in.
Oh, it's strong.
I didn't
You gotta waft it. Now stick your nose.
Waft. What do I do? What do I do?
I made it at a 0.2. So I had one group that was a little low and 3 that were high on their calculations. Please think back through what you did to make it that way, what error could have occurred. If you can tell me what error could have occurred, then it'll make sense. And the lab, I call it good. Hydrochloric at 0.2, you took the volume of that, you multiplied it by the concentration, and that should equal, at the equivalency point, the concentration and the volume of your base. Now to solve it, what I asked you to solve for was the molarity of the sodium hydroxide. So you can just cancel out the volume from either side by dividing either side by 25. So there's your answer, just putting in what you measured in milliliters right there. I didn't make you convert this to liters. If we were going to take this into moles and into grams from there, or even into particles, we could even get the number of particles of sodium hydroxide that were in there. But I chose this because no coefficients, no real stoichiometry at all. Now, I did find a new guy to listen to. Please be paying attention. Put that away. And he's from Texas, and his name's Mr. Causey. If you would pull that video up for me there, Carly, and put it up.
We know that during titration, it took 41.56 milliliters of sodium hydroxide to reach the endpoint. So we need to know the molar ratio, and the molar ratio is 3 moles of sodium hydroxide per 1 mole of phosphoric acid. And we need to remember that it's a 3-to-1 relationship there. So let's lay out a plan. And that plan is going to be first to determine the moles of sodium hydroxide used, and then determine the moles of phosphoric acid. We'll then find the molar mass of the phosphoric acid. And with that, we'll calculate the mass of phosphoric acid. Won't be too difficult. So first, let's do the mole calculation for sodium hydroxide. There's our moles. And remember that molarity means moles per liter of solution. All we have to do is multiply that by the milliliters. Now, we're going to need to change the milliliters there to liters. So let's do that. And we'll move the decimal 3 places to the left. Cross out our liters. Then we're going to plug and chug. And here's our answer. Using 4 sig figs, we get 5.045 times 10 to the negative 3 moles sodium hydroxide. Now let's do moles phosphoric acid. We know there are 5.045 times 10 to the negative 3 moles of sodium hydroxide. We also know that there's a 3-to-1 relationship of sodium hydroxide to phosphoric acid. So what we'll do is we'll use that to convert. And note that I've put it in such a way our moles sodium hydroxide cancel out. We can now take that and plug and chug it. And voila. All right, let's go to the next step. Molar mass. Well, to figure out the molar mass of phosphoric acid, what we want to do is go to the periodic table, and on the periodic table find hydrogen, and that's about 1.01 grams per mole. Then find phosphoric acid, and that's about 30.97 grams per mole. Then find oxygen, and that is 16.00 grams per mole. And notice now I'm using about 2 decimal places on all of these because that is my usual take in the classroom. So that's what I'll do here as well. Now, let's go back to our blackboard. Write all the values down. Go ahead and plug and chug. And there's our answer, 98.00 grams of phosphoric acid per mole. Now we can use that to help us determine the mass. We know there are 1.682 times 10 to the negative 3 moles of phosphoric acid. Multiply that to the moles or grams per mole. And cross that out. Plug and chug. And we have our answer. 0.1648 grams of phosphoric acid is what we have. Great. Let's recap. You calculated the moles of sodium hydroxide and phosphoric acid. You determined the mole ratio, and then you found the molar mass of phosphoric acid, and then you calculated the mass of the H3PO4 present.